So welcome, I'm Salvatore, and today I'm going to discuss network-accelerated non-contiguous memory transfers, which is joint work between us, Cray, and the ITED department at ETH. So before starting, let's see what we mean by a non-contiguous memory transfer. So usually when we distribute an application, we start with some domain that we need to distribute among multiple nodes. So we end up with something that looks like this. So here we have the nodes, and then depending on the application and on the partitioning we choose, we have to communicate some data, and this data is basically domain or the evolution of the domain as it goes with the progressing of the application. So then what happens is that on one node, we are going to send some data, and this data in memory of this one node will look like this. So the blue boxes, for example, are the ones we want to send. So usually what we have to do is to pack this data, so these blue boxes, in a contiguous buffer, and then send it. Then the receiver will receive this packed buffer, and it will have to unpack it. So this is like how at high level this works. So non-contiguous memory transfers are we can have multiple types of them. So like structured exchange, where we basically always know the type of transfer we are going to have. So we always know like the portion of the memory we want to transfer. And this is the case of, for example, seismic waves propagation. Another example is reshaping, where we have the data we want to send at the center in some layout. And the receiver says, okay, whenever I receive this data, I want you to copy this data in this different layout in my receive buffer. And this is the case of fast Fourier transform, for example. The third case is unstructured exchange, where basically the layout of the data we want to send depends on the data itself. And this is molecular dynamics. So as we can see, there are like multiple applications where we can be faced with this type of transfers. And in fact, this is well recognized. We have support for this kind of transfers in multiple languages. And this support varies from IO vector to compiled assisted aggregation and so on, right? Or derived data types in MPI. In fact, in this work, we will focus on MPI and derived data types, just because it's the more general way to express arbitrary layouts. But actually, all the things we discuss here can be applied to these other supports and languages too. So just to give a brief overview of like MPI derived data type. So assume we have this memory here. Again, the blue boxes are the ones we want to send. And then we can start describing this memory like this. So here we have a vector. So we have a nice structure where we have fixed block sizes. So 2, 2, 2 with some stride that is fixed, always the same base, right? On this other side, this is not so structured. And we can say that this is an indexed data type. So this means that one block will start at this point here, then one block of size 2 will start here, and so on. And then we can say, okay, now this whole thing is a struct composed by a vector and an indexed data type. Okay, so you can really like build your data type and hence describe your memory layout arbitrarily. And then you give this to the MPI implementation, and the MPI implementation will make sure of doing this packing and unpacking as we described. So let's see how this works, again, like assuming a kind of naive implementation. So here we have the sender on the top and the receiver on the bottom. And basically what happened in this work, we focus only on the receiver. If you have questions about the sender, we can discuss them later. So what happens is basically that you receive the packets of the data you are receiving, of the message you are receiving, and they are copied in an input buffer in the host memory of the receiver. However, at this point, the transfer is not completed yet. In fact, we have to interpret now the data type that the receiver tells you, and copy the data to the right location in the destination memory. So basically, we have to read this data, process the data type, and finally copy it to the right locations in the receive buffer. Okay, so now if we want to like show the performance of this kind of transfer, here we have the throughput on the x-axis in gigabit per second, and on the y-axis we have the block size. So this is a benchmark for the vector data type. So, and the block size basically gives us an indication of how complex is the data type. So for small block sizes, we have something like this, and again, the blue boxes are the ones is the actual data. And now you can see that for each block, basically, we need to make a mem copy. right? So while if we keep increasing the block size, we have fewer and bigger contiguous regions. So we have to do less copy. So the processing of the data type gets simpler. Now, if we plot this, the throughput achieved by the approach I showed before, so that we call host-based data type processing, this is what we get. So here we are receiving data at 200 gigabit per second, but however, we are able to process the data type at almost 75 gigabit per second. So we are not so happy with that. So now the question is, can we accelerate this data type processing by offloading this processing to the network cards? And for this, we use SPIN, which is a programming model that allows the user to express some kernels that we call handlers. And these handlers then are run on a per packet basis directly on the NIC. So we will see how it works in a second, actually. So where SPIN sits in a NIC. So this is a general model of an RTMA NIC. So we receive the data from the left side, basically, and while here on the right side, there is the host memory. And we receive the packets. The first thing we do is we receive them in the inbound engine of the NIC. Okay, the inbound engine will parse the packets and do some basic work. And then we have this matching unit here, and inside this matching unit, we have what we call matching entries. So this is a term we borrow from Portals 4, but basically you can imagine that for each MPI received, you have an ME that you install in this matching unit. And in fact, you can see that an ME contains some matching bits that are basically the MPI tag, can be related to the MPI tag, and also like the memory address of the receive buffer. We extend this concept and add these spin handlers. So in this case, these are pointers to this memory here that just point to the functions that are the handlers we want to execute. So basically what happens is that you receive a packet, you get an ME if there is a matching. And if there are spin handlers associated with that ME, then the inbound engine will forward the packets to the NIC memory in order to be processed. And how they are then processed, we will see that in the next slide. Otherwise, if there are no spin handlers, then the packets and the data will take the classical non-processing data path, where the data will be just DMA'd to main memory without no further processing. So now, how it works inside this, what this unit does. So basically, to describe SPIN, we use an abstract machine model where we have our NIC, and then inside the NIC, we have a fast shared memory, the NIC memory, and then packet scheduler that we will see in a second, it in action, and a set of HPUs or handler processing units. So these are just cores, so like the ARM cores, you can think to them as ARM cores or RISC-V cores. Then we have a DMA unit that allows SPIN to communicate with the host memory, right, to move data to and from the host memory. And at this point, the host CPU asks just to upload the handlers that you want to execute for each packet to the NIC memory in order to be there when packets arrive, and also to manage this memory. So basically, whenever we get packets from the inbound engine, remember the previous slide, what happens is that they get forwarded to the NIC memory, and the packet scheduler decides on which HPUs they have to be executed. Now the HPU the handlers running on the HPU can consume the data, or like in this case, maybe transform the data and then move it to the host memory. So this is now application specific. The processing we do is application specific. So this is now like a brief introduction to SPIN, but now the question is, how do we use this to accelerate non-contiguous memory transfers, right? So the first approach is let's define a simple data type as an example, and in this case, this is a vector, and have a description of it. So here, number of blocks, the block size, so two squares per block, and the stride, and so on, right? Then we write our own handler. So this is now the handler, the code that we want to offload to the NIC, right? And should be able to then copy the receiving data in the right position. So what we do is we move this description here to the NIC memory. We move also the handler to the NIC memory. And then the idea is that for each packet that comes, we will run this handler. And this handler, basically, the things that it does is, okay, load some data type information, so basically here, that are here, understand where this packet is or starts inside the receive buffer, and then you have to take into account that inside a packet, you could have multiple non-contiguous memory regions, right? I could have a 2 kilobyte packets and like 4 bytes blocks. Okay, so I will have to do multiple DMA writes, right? And then for each non-contiguous region that we find inside a packet, we just DMA this packet or the specific non-contiguous region to the right location in the receive buffer. So now, how about the performance, right? So if we look now at the throughput we get with this approach, then we are kind of happy because after 64 bytes block size, so this is always the same benchmark of before, we are able to reach line rate. So here we plot the nominal line rate, but since there is some space overhead inside the packet, you cannot achieve that really. Okay, so this is like the ideal case. Right. So, but however, we discussed that MPI data types can allow you to express arbitrary layouts. So this can get quite complex. And like the example we discussed just now was for a simple vector data type. Right. So, and then this means that every time you come up with a new data type, so you build your own data type, then you have also to write your own handler, and this can get quite complex. Okay. So now, the question is, can we have a general handler that we can use for any data type, right? In a way such that the application or the user doesn't have to write its own handler for each data type, right? And obviously, I mean, we want some solution that also approaches the performance of the specialized handlers. So how do we do that? So the idea is to start from the MPI types library. So this is now a library that moves the processing of the data types outside MPI. And if you think about it, this is exactly what this goes in our direction, because we are taking the processing of data types and moving it to the NIC. And we really don't want to run the full MPI implementation on the NIC, for example. So we want something lighter. And the idea now is that given some layout, right, we can start describing this layout. Like in this case, we have 2 vectors. So this cannot be a single vector because here there is arbitrary space. And you see that we have a description of the data type here. We have, in this case, of just this vector. This is very similar to what we have seen before. And then you build up an hierarchy. So basically, and these are called data loops, actually. So in this case, this is an index of 2 vectors. And then you will have this hierarchy that says, okay, this is the index, and you describe the index, and the leaf then is the vector. And finally, you have the base type that tells you like how big is each one of these squares. An additional data structure that this library uses is the segment. So the segment is like something that stores the current processing, the current state of the processing of the data type. So we will see this in action in a second. And the idea is, let's keep this, the receive buffer has to be on the host because it's used by the application. And these structures here, we need them on the NIC in order to like process the data type directly there. And now the idea is, okay, we receive the first packet and we run this MPI types library on the NIC. And basically now you see that this just, like you can see it as a progress bar, basically. So we are filling the first vector now. Now the first vector is filled up. And this means that the half of the index is also filled up. And so we go on with the second vector, and we finally finish the processing of this data type, right? So this is important because this allows you to basically like restart the processing of the data type from any point. So you can exit from the library and then resume the processing later. And again, this is good for us because we need to resume, right? For each packet that we come, we don't get the whole message, we get the single packets of the message. Okay, so in reality, this is a bit more complicated because we have multiple HPUs running in parallel. So the first 2 packets, you can be lucky, they run well, but for example, the second pair of packets, they run in parallel. This can happen, right? You have multiple handlers for different packets running in parallel. And now since we are updating this segment data structure here, we have write conflicts, and this can screw up the whole processing at this point. Okay, and basically we don't want to synchronize because like to locking this data structure here, because this would risk to like serialize the whole processing. So we are going to explore solutions that avoid this synchronization here. Okay, so the first solution we propose is what we call HPU-Local, and the idea is pretty simple. So it's let's just like duplicate the segment for each HPU. Okay, so now each HPU will have its own segment. So this means that the first packet comes, HPU 0 will use only segment 0, and this goes on, right? So this seems to work pretty well. However, as you go a bit forward, you see that now HPU 2, in order to like get to this green block here, that is the state that is needed to process this third packet, has to do some fast forwarding. Right. So it has to reach that state because it will find that segment uninitialized, right, or in its initial state. Okay. So we call this fast forward overhead, and this is basically proportional to the number of HPUs you have if you assume that if you assume round robin scheduling. But this is a bit problematic in terms of performance. In fact, if we plot the throughput reached by this solution, we have something like this. So for large block sizes, this is fine. It actually approaches specialized. And this is because for larger block sizes, as we discussed before, the data types is simpler. Okay, so this means that also like this fast forwarding overhead will be smaller. So because it will be easier to catch up, you have less less contiguous regions basically. But whenever like you have multiple blocks, then again this fast forward overhead dominates and basically gets you this performance. So at this point, it's basically not convenient to offload the data type. You can just process it on the host, right? So how can we improve this? So the idea is, okay, let's take a step back and go back to the host. So let's have some pre-processing of the data type, basically. And the idea is, let's build some checkpoints or snapshots. So, so without the data, okay, we just run the data type processing. It's like a dry run of the data type, and we fix a checkpoint interval. In this case, what corresponds to 2 packets data, and then we have the first checkpoint, the initial state. Then we receive the first 2 packets. I mean, again, we are not receiving. We are just like acting as we are receiving them, but actually there is no data moved here. We are just building these checkpoints. We will see why we need them in a second. And yes, then we have this set of checkpoints here. And now the idea is that when you get the packets, the first 2 packets will use checkpoint 0, but the third packet can use directly checkpoint 1 because it will find already like it can resume from this state and basically pay 0 fast forward overhead. Okay, and so on. So now, how do we use them? So the idea is, let's move all these checkpoints to here are called snapshots, but they are the same thing, and to the NIC memory. Okay, and so whenever we receive the packets, then packet 1 will use snapshot 0, and second packet will use again snapshot 0. But now you see again the problem, because again these 2 handlers can run in parallel, and you have the write conflict. So like a naive approach to using snapshots on the NIC also doesn't work. So the solution is to use read-only checkpoints. And in this case, what we do is basically we receive the packet, and the HPU getting this packet, we just make a local copy of this snapshot. Okay, and at this point, we just solve the write conflict problem because each HPU will write to its own copy. And actually, then we don't write back, because then for writing back, we will need to synchronize again. Okay, so if we plot now the throughput of this solution, we see that it does better for like small block sizes because we limit this fast forward overhead. However, for larger block sizes, now there is no way we can reach specialized because we introduced this copying overhead, right? For each packet, we need to make a copy of this snapshot, and then this is going to limit us. So So again, so basically what we wanted is something that still is able to update the checkpoints, but avoids the write conflicts. And this is the final solution we proposed. We call them read-write checkpoints. And the idea is basically to introduce a new concept in Spin that are the virtual HPUs. And these virtual HPUs, you can see them as kernel threads, basically. And whenever a packet comes, now packet 1 is associated with virtual HPU 0. Okay, because virtual HPU 0 has the ownership of snapshot 0. And this virtual HPU now gets scheduled to a physical HPU, okay, and will run this, will process this packet, right? So the second packet now will again be associated with virtual HPU 0. So it will be not scheduled on another physical HPU, but it will be queued up on HPU 0, basically. Okay, so what we are doing here is basically serializing like the processing of the packets of groups of packets in order to like avoid these write conflicts. And yeah, so they don't really have to be tied to the specific physical HPU. So if we plot now the performance of read-write checkpoint, you see that we actually approach specialized, and the big difference now is that we are using an generalized handler, right? So we don't need to write our handler for each data type, but we just have one, and what changes is basically the data structures we build. Okay, and the important point is that you build these data structures per data type and not per message. So you can build them once and then reuse them. If you reuse the same data type for receiving multiple messages, you can reuse these data structures. Basically, you don't have to build them again. Okay, so this solves like the performance issue, and now the question we are left with is how about this checkpointing interval, right? Because now you can think of, okay, now you are going to blow up the NIC memory with all these checkpoints, so this is not nice. So how do we reason about this checkpoint interval? Let's visualize the packet's arrival in a slightly different way. So in this case, we have just 3 HPUs. Time is here. And we receive the first packet. Now the color tells you the checkpoint they are going to use. So this will be scheduled on HPU 0. So the rectangle now is the virtual HPU, right? The second packet now arrives, and it cannot be scheduled, right? It has to be buffered because the virtual HPU 0 that owns this packet is already scheduled, so it's already running. Okay, so you get then the third packet. This is associated with a different snapshot, hence a different virtual HPU, so it can be scheduled immediately. In the meantime, this HPU 0 finishes, so it can start the second packet, and so on. So the point is that you fill up this pipeline, and here you can see that we have some delay to start utilizing the full system. Okay, and this delay also depends on the checkpoint interval, right? Because the bigger the checkpoint interval, and then also the bigger this will be this delay here. So basically the message here is that if you use a single checkpoint, okay, you are going to serialize the whole packet processing, the processing of all the packets you receive, and this will not be cool, right? So then the way we decide the checkpoint interval is we model these timings here, and what we want to do with this formula that I'm not going to explain is first limit the impact of the scheduling overhead. So our goal is to minimize this guy here, but also we do not want to saturate the NIC memory. So the number of checkpoints we build, they have to fit in NIC memory. And finally, we also do not want to saturate the NIC, the packet pattern, because remember that here we are buffering packets when we cannot process them directly. Okay. So for the evaluation, we use the Cray Slingshot simulator. So Slingshot is the latest interconnect from Cray, now HP, and they simulate this on Sandia SST. So we extend this simulator with Gen 5. Gen 5 now is a microarchitectural simulation, and we use that for simulate the handlers that we run in Spin. So in this simulation, you can really write your C code describing the handlers, and this will be timed using Gen 5. And we model like a Spin unit with 32 HPUs, and each HPU is an A15 core running at 800 MHz, and we assume single cycle access memory, like this NIC memory we have seen in the abstract machine model before. So the main result is basically we select a set of applications. Here is just a subset. We have more in the paper, and then for each application here is represented by a tile. And inside each tile, then we have multiple data types that are used by this application. And for each data type, sorry, it's a bit convoluted maybe, we have like the speed up that the different versions provide with respect to the host-based data type processing. So basically this means that like the generalized handler, so the read-write checkpoint we have seen last, will have a speed up of up to 10x and a bit more for this application over the host-based processing. So no offloading basically. So just packing and unpacking. This bar here, this orange bar is the specialized version. So what if I write my own handler for this exact data type? And then this violet one is data type processing with portals for using IOVX. So then we have multiple applications, as we said, but the takeaway message is that on average, by offloading data type processing on the NIC with spin, we can have 5x speed up with respect to non-offloaded versions, and this goes up to 11x in some cases. And the performance of the generalized handler is comparable with the performance of the specialized handlers, so the ones that are tuned for that specific data type. And here we can see that in some cases it doesn't make any sense to offload data types to the NIC. And this is because, for example, the messages are too small, so you basically don't get enough packets to exploit the parallelism you have on the NIC, and you are just adding some latency then. And the other reason is that maybe you have too many non-contiguous regions, right? So if the block size is, to make the example of before, if the block size is too small, then for each packet you are going to make a lot of DMA writes, right? So if I have a 2K packet and my block size is 4 bytes, then I'm going to have 512 DMA writes of 4 bytes for each packet, and that's not efficient. Okay, so we have more deeper analysis in the paper. For example, one question is, we said that we need to perform some pre-processing right in the beginning to make these checkpoints and offload them. But then how costly is this? So what we find out is that in the 75% of the cases we analyzed, after 4 reuses of the same data type, you can amortize this cost. So again, this is, remember the discussion of before, you can reuse then the same checkpoints for different data types. If we look at data movement, so basically the data that is moved between the NIC and the main memory, and the main memory and the CPU memory hierarchy, so caches and registers, we see that by offloading the type processing, we move up to almost 4x less data. So because basically now we are avoiding this movement here, because we don't have to process the data type on the CPU and then copy it to the right locations. And yeah, we have more detailed analysis that I'm going to skip here for time reasons. So before concluding, I just want to glance at the ongoing work for which we have some preliminary results here. So until now we showed spin on simulations, but the question is, okay, fine, but how can we implement this on real hardware, right? And for this, we are collaborating with ITET. We are using the PULP architecture. And the idea now is that we have multiple clusters. Inside each cluster, we have a set of RISC-V cores and a fast shared memory. So this is a scratchpad actually, and it's really single cycle access. We have multiple of these clusters, and all the clusters are interconnected between themselves and with an L2 memory. So this is a bigger scratchpad. Again, these are scratchpads, so no hardware caches, because we want to keep the architecture simpler. Also because we want to have predictable handlers in terms of performance. And then what we do basically is interface the NIC, the inbound engine. If you remember from the beginning, the inbound engine is pushing the packets to the spin unit if there are spin handlers. So it will push the packets directly to L2, right? And then this the clusters here, the processing clusters, will just fetch packets to process and execute the given handlers. In fact, the host is also connected to this interconnect with PCIe and can write the handler's code, for example, and manage the memory directly in L2. And then finally, we have also the common queue of the NIC, but let's skip this. So just to conclude on this part, we synthesized this architecture at 22 nanometer, and we were able to close the synthesis at 1 gigahertz. So these cores are running at 1 gigahertz. The total area that this architecture takes is about 100 megagate equivalent. That corresponds to 23.5 millimeters squared. And basically, most of the area, so here is the total area that we have, is taken by memory. Here you see the clusters, the area taken by the clusters, and basically 60% of the area is taken by memory. And here is a zoom of the cluster, and you see again that most of that is taken by the L1 memory, so this scratch pad here, and the cores take a very little area. If we want to make a comparison, then we can consider Mellanox Bluefield, which has 16 cores, but they are bigger cores, and like the area taken by these cores for processing is about 51 millimeters squared, so almost double. And if we would have this area, then we could fit 64 cores. We always consider 32 cores in our tests, and also 18 megabytes of memory. So the full power, the power consumption that we estimate is about 6 watts under full load. And like again, if we now see the same experiment of before that we carried out during the whole talk, so about this strider data type, now we see that we are well over the 200 gigabit per second if we run on pulp. So again, this is now not limited by the network. So this is assuming, okay, let's assume that we have all the packets already in these memories, and let's see what's the maximum throughput we can achieve, right? So this makes this architecture like a first-class candidate for implementing spin. Again, here there are 2 different versions, but details are on the paper. We can discuss them later. Okay, so to conclude, we presented how to accelerate non-contiguous memory transfers. We motivated like their existence and why they are important, and showed like different ways to offload their processing to spin. And finally, we showed some results and also like discussed a bit what's next in this project, and you will hear from it soon. So this concludes the presentation. I'm happy to take questions.